Hello everyone, this is going to be a little walkthrough of the 2021 Level 2 Mechanics paper for NCEA Level 2 Physics. I'll try and highlight the Achieved Merit Excellence points, but yeah, we'll just get straight into it. Make sure you've got your resource sheet, your equation sheet to hand, and a calculator and a pencil would all be useful as well. So we'll go, just make a start. So question 1, we have the ramp. We are told that the picture on the right shows a bike rider going over a ramp. The rider's speed at the top of the ramp is 10 meters per second. The angle between the ramp and the ground is 30 degrees. The top of the ramp is 1.1 meters above the ground. And we have ourselves a little diagram given to us already. Part A, question A. Show that the vertical velocity of the rider just as they leave the top of the ramp is 5 meters per second. So immediately we're looking for the vertical velocity. Now we know that we've been given an angle and the overall speed of the cyclist, and so if we just add a couple more sides to this triangle, filling in the 30 degrees, we know that we are after this opposite side for the vertical component of the cyclist's velocity. Therefore, the equation from SOHCAHTOA that involves the hypotenuse and the opposite is sine theta. Sine theta is equal to opposite over hypotenuse. Now we're interested in working out what the opposite is, so I'm going to multiply both sides by the hypotenuse to get an equation for the opposite, where the opposite is equal to hypotenuse multiplied by sine theta. And then just put my values in. 10 sine 30, and put that into a calculator, making sure I'm in degrees, not radians, and I should get the answer of 5 meters per second. Because it's a show that question, this is only worth an achieve mark. Part B. Calculate the maximum height that the rider will reach above the ground. So we've just been asked to work out our vertical velocity, and we're going to use that again in this part B. If you're unable to do part A, whatever answer you get here, if you use that in your working for part B, you'll get credit, even if it's not the right answer to part A. Although because it's a show that, hopefully you did get there. Working out the maximum height, we're going to use our kinematic equations of motion. And so, before we do anything else, because I know I've been given some distances, some velocities, and I know what gravity is, I'm going to jot down my d, vi, vf, a, and t. And I'm going to go through and sort of fill in what things we either know or what we're trying to find. Now we're being asked to calculate the maximum height that the rider will reach above the ground. Therefore, I'm looking to find my distance. My initial vertical velocity, because we're talking about maximum height, we're interested in the vertical velocity, that's going to be the 5 meters per second that we've just worked out. Because at the top of his jump, if he has a path sort of like that coming off the top of the ramp here, when he gets to the midpoint, the highest point of his journey, his vertical velocity will be 0 meters per second. And so my VF is going to be 0 over here. Gravity is a constant on Earth, acting downwards, because I've said that my upwards direction is going to be my positive direction. I now have 4 values. I'm going to choose the right equation from my equation sheet, rearrange it to get D on its own. So pause here and have a go at the question. If you haven't already, I'm going to continue on. The correct equation from the equation sheet is Vf squared equals Vi squared plus 2AD. I want to rearrange this to get D on its own. So I'm going to first of all drag my Vi squared over onto the left hand side. That's equal to 2AD. I want to get the D on its own, so I'm going to divide both sides now by 2A. And that gives me an equation for my distance. And then simply put all the numbers in from this little table I've done up in the corner, and I work out my distance. My VF was 0, 0 squared minus 5 squared divided by 2 lots of minus 9.8. If we throw that into a calculator, we get 1.2755 ... and we're going to round that to 1.28 meters. Okay, now that's how much height the cyclist gained from the top of the ramp. He left the ramp at 5 meters per second with a vertical velocity of 5, and so we have to remember that when he's left the ramp he's already 1.1 meters above the ground. The question is asking for the height he will reach above the ground, and so I have to add the top of the ramp's height, 1.1, to my answer. Height above ground equals 1.1 plus 1.28 equals 2.38 meters. Final answer. If you work out 1.28 meters and stop there, that is achieved. If you made a mistake with your calculation here and you got a different answer to 1.28 but tried to add it to 1.1 either way, that's still achieved. You get merit only if you get the full final answer of 2.38 meters like that. Now, part C. The diagram below shows the path of the rider when they leave the top of the 30-degree ramp at 10 meters per second. As you can see here, this is why we draw in pencil. I've drawn it without really reading the question properly, but because I did it in pencil, I can rub it out and redo it. So, we have an increased angle from 30 degrees to 40 degrees, and so the start of my arc is going to be slightly above the original line of 30 degrees. Because he's got a higher angle, his vertical velocity initially was higher. Therefore, he will go to a higher distance. And because we're still below that 45-degree cutoff, it's going to extend the path of the horizontal distance travelled, rather than the mistake I made where I shortened it. If the angle had been increased beyond 45 degrees, that's where you can start to get higher distances but then shorter horizontal distances travelled. If it stays below the 40, it just gets longer and longer. So something like that, where you have a higher maximum peak and it lands further to the right. If you did a parabolic shape, so a nice curved shape that goes higher with a peak that's slightly higher than the maximum peak of this arc here, with a greater horizontal distance and the same starting point, those 5 things, if you got them all, that's merit. If you only do 3 of those things correctly, or 4, it's achieved. If you only manage to do 2 or less than of those 5 things, it's not achieved. Okay, so part D. For a rider leaving the top of a 30-degree ramp at 10 meters per second, you are going to calculate the vertical speed of a rider when they land on the ground. Okay, so when the rider was, because of the way that we assumed that there are no external forces, there's no air resistance, there's no friction, in the case here, if he's leaving the ramp with a vertical velocity of 5 meters per second, symmetrically speaking, when it gets to this point here, because there are no other forces acting on him other than gravity, the cyclist will have a velocity of a vertical velocity of 5 meters per second acting downwards this time. We then just need to work out how much extra velocity is gained by him as he falls from here 1.1 meters down, remembering that that's how high the ramp was above the ground. So again, if we start by writing out our 5 different values, we know that gravity is minus 9.8. We are trying to work out the final velocity. He's starting from minus 5 and he's travelling 1.1 meters downwards. Now, because I always have downwards as negative, all of my values here are going to be negative. If you have gravity as positive, then all of these will be positive. The answers will be the same, whatever way you decide to do it. Now we want to work out VF. We're going to use the same equation as before. VF squared equals VI squared plus 2AD. But this time we're trying to work out VF, so there's very little rearrangement we're going to do. Just going to square root the entirety of both sides to leave me with VF is equal to the square root of VI squared plus 2AD. You have to have the VI squared plus with the 2AD inside the square root. You can't square root this individually, then just have 2AD square rooted after the fact. They have to all be in here together. Then we throw in our numbers and start typing it all out. So minus 5 squared plus 2 times minus 9.8 times minus 1.1. And if you do your negative signs wrong, you'll get a math error for trying to square root negative numbers. 2 times 9.8 times 1.1. Put it in your calculator and you should get an answer of 6.8234 ... and we'll round it to 6.82 meters per second. Okay. Now, part 2 for question D is calculate the horizontal distance travelled from the ramp to where the rider lands on the ground. So now, we're going to have a case. We're going to still only consider the vertical velocity because we need to work out how long this journey took. Now, we can't work out the duration of this flight through the air from just the horizontal motion. Sorry, the sun's come out. I'll try and get rid of that shadow. There we go. So you have to work out the vertical motion, or deal with the vertical motion first in order to work out time. So I'll have a little time vert motion to begin with, then we can work out horizontal distance afterwards. So, to work out the time that the cyclist is in the air, we're again going to use our D, VI, VF, A and T. Now there are a number of ways to go about this. I'm going to try and do it the way that I think is the easiest. If we consider his starting motion at the top of the ramp, by the time he then lands on the ground, he would have fallen by 1.1 meters. He started off going upwards at a velocity of 5. I'm going to use my acceleration due to gravity as minus 9.8, and my t is what I would like to find. Okay. Now, if we go down this road, we're going to get a quadratic equation. But, alternatively, if we use our VF that we've just calculated up here, instead, minus 6.82, we now can choose any equation we like. I'm going to go with the first one, VF equals VI plus AT, and we're rearranging this to get T, so I'm going to subtract VI from both sides, VF minus VI equals AT, divide both sides by A to get an equation for T, which equals VF minus VI divided by acceleration. If I then substitute my values in, my VF was minus 6.82, my initial velocity was positive, and so I just have minus 5, all divided by minus 9.8. And put that on a calculator, minus 6.82 minus 5 divided by minus 9.8. And I then get a time of 1.206 equals 1.21 seconds. So now I have my time. I can use velocity is distance divided by time, rearrange the distance, which equals VT. Now I don't know what my horizontal velocity was yet, so I need to go back to the very first part of this question where I was doing my trigonometry to work out the vertical speed. Same idea, but this time I need to work out the horizontal one, which is my adjacent side. And so I'm going to be using cosine instead of sine. So cosine of theta is equal to the adjacent over the hypotenuse, therefore the adjacent is equal to 10 cos 30. Now I'm going to work out whatever that adjacent side is. Sorry, it's off the bottom of the page. So I do 10 cos 30 gives me 5 root 3 equals 8.66 meters per second. So then my distance is equal to 8.66 multiplied by 1.21. I wasted a lot of space in my answer box, but I get an answer of 10.478, which I'm going to round to 10.5 meters. Okay. Now there are going to be some various rounding errors you can get here. Just checking against the mark scheme. Their calculations give me a different answer. Hang on, 8.66 times 1.21 is a rounding error, and the mark scheme doesn't appear to have rounded their answer correctly. So if you get 10.5 and then the answer says 10.4, I think you're still correct anyway, or more correct than the answers are. Now, if you get all the way through it and get to the final answer, that is excellent. There's a lot to do in this question. If you go up to the time of 1.21, or you got to the quadratic equation instead of using minus 6.82 as your final velocity, if you got to a quadratic and got stuck, then you get merit. Or if you did all this, or tried to do all this and made one error in it and carried it forward, that would be merit. If you find your the final velocity is 6.82 from the previous part, that's achieved. Or if you've worked out this horizontal velocity of 8.66, that is also achieved. There's a lot to do here, but the achieved marks are just for doing part I and for working out this horizontal velocity. And that's question 1. Okay, question 2, around the bend. A rider rides around a circular bend of radius 7 meters at a constant speed of 10 meters per second. Don't know what the picture was here, don't think it's that important. I'm just going to add a quick diagram. The center of my curve here, I'm going to say that his velocity is 10 and the radius is 7 meters. Okay, just to help visualize it. Now, if the combined mass of the rider and the bike is 90 kilograms, calculate the centripetal force required for this rider to go around the corner. Looking at our equation sheet, Fc is equal to mv squared over r. I've been told the mass, I've been told the velocity, I've been told the radius, so all I have to do is throw everything into the equation and type it out on my calculator. Times 10 squared divided by 7 equals 90 times 10 squared over 7 gives me 1285.714 which if I round it goes to 1290 newtons. Okay. Now part B. When the rider is in the position below, they bike across a very slippery part of the track. Use physics principles to explain the path that the rider takes when they bike across the very slippery part of the track. Show this path on the diagram with an arrow. It doesn't say it explicitly, but the assumption is if you read that they go across a very slippery part of the track, this statement essentially means friction is 0 newtons. It doesn't say it, doesn't say that there is no grip anymore, it says it's very slippery. We have to assume that the friction goes to 0. If there is no longer a friction force, there is no longer a centripetal force. Therefore, the rider has nothing accelerating it towards the centre of the circle, and so he'll just go off in a straight line at a tangent to the circle. Okay, we now need to explain that, and we have to explain that fully, basically, to support our answer. The diagram itself is not enough, you do have to give a full description of what's happening. So, on the slippery part of the track, sorry, you should probably pause it if you want to have a go at this yourself here. On the slippery part of the track, there is no friction. No friction, and therefore no centripetal force. This means that the rider will continue with a constant velocity. Now he's stopped accelerating towards the centre. A constant velocity at a tangent to the original circle. Okay. Now, if you applied a more realistic interpretation of the question, and instead of saying it was a straight arrow, you just shot off straight, you said it was a much wider curve because there would still be some friction, and you absolutely do get credit for that, as long as your descriptions are adjusted from what I'm going to say in a sec. If we've got this diagram, we're saying he's going straight off, there is no friction. You have to say, for merit, something about there being no centripetal force, or there are no longer unbalanced forces. There's no reason for him to turn inwards anymore, basically. The second thing you have to say, or two different things you have to say, there are three things to choose from, sorry. You have to say at least two of them. That being, that he carries on at a constant velocity, at a tangent, and is going in a straight line. If you say any two of those things, along with this point up here, that's merit. If you just say two of these things, or if you only say two of these things without mentioning the centripetal force no longer existing or being smaller, then it's just a G. And it's the same sort of pattern if you had said there was a wider curve rather than a straight line. But that's question 2B. Now, question 2C. Some trail bikes have a spring suspension system. The spring constant is 40,000 newtons per metre. A rider of mass 80 kilograms sits on the bike, causing the spring to compress. Calculate how much energy is stored in the compressed spring. Okay, now the equation on our formula sheet, on our resource sheet that we have for the energy of a spring is elastic potential EP is equal to half kx squared. Now we don't know what this x is, and so at the moment we're unable to work out the elastic potential energy. Now we do know how heavy the rider is and that he's sitting on the bike. If you're sitting on something, that means you are letting gravity pull down your mass. And so if we consider the forces, by considering forces, we have an equation for the force, for the weight of the man, but we also have Hooke's law, minus kx, which allows us to calculate the force required to compress that spring. Okay? And you see here, now we have a letter x that we can work out from mass, gravitational field strength, and the spring constant. So if we say that mg is equal to minus kx, and we divide both sides by minus k, we get mg over minus k equals x. And if we substitute those values in, he's 80 kilograms, gravity is minus 9.8, and our k is 40,000. Remembering the minus, because we've got a minus on both sides, they will cancel out. You work out your answer to that in your calculator. Over 40,000. So we have an extension of 0.0196 meters. Okay? Or 1.96 centimeters, 196 millimeters. Now we can throw that into our potential energy equation. EP equals half kx squared equals 40,000, half times 40,000 times 0.0196 squared getting an answer of 6.7832 32, which we can round to 7.68 joules, because this is an energy we have just calculated. Okay? Now, part D. When a rider lands after... Sorry, I should have said. If you did both parts of this, working out the extension and then the energy correctly, that is merit. If you did one of these calculations correctly, you get achieved. You can do this one correctly even if you have the wrong value for the extension. So if you made a mess the first one and still carried on, you can still get the achieved credit. Now, part D. When a rider lands after a jump, they essentially have a collision with the ground. Use physics principles to fully explain how a suspension system makes a bike safer for landing. Now again, as soon as you're dealing with a problem where something is coming to a stop and there's something there, whether it's an ice hockey player and his padding, obviously a suspension system and a bike, we're thinking about the collision, the impulse equation. From our equation sheet, we have the impulse equation that F is equal to delta P divided by delta time. So the force experienced by something is equal to its change in momentum divided by the time elapsed for that collision to take place, essentially, the change in time. So these are the physics principles that we are going to refer to. Now, with or without suspension, I'm going to claim that the change in momentum is a constant. Delta P will be the same. Not having suspension doesn't stop you falling any slower, and so he'll hit the ground with the same speed and eventually come to a stop, whether or not he has suspension. Comfort is different, the force he experiences is different, but the change in momentum will be the same. Suspension, or the spring, suspension increases the time taken for the rider to come to a stop when he's landing. So the suspension increases the time taken for the rider to come to a stop while landing. And the reason I've written down that equation straight away is if delta time increases and delta P remains constant, then the force experienced will decrease. Therefore, the landing will be safer. Okay, and so if you make an answer that's as full as that, that will be excellent. If you make essentially one of these different, or two of these different points, that gets you merit. So if you'd said suspension increases time taken, if t increases and force gets smaller, then that'd be merit. If you include the delta p staying constant, then that's enough for excellence. The last point here, you do have to answer the question that's asking, does it make it safer or not? You're asked if it makes it safer, so you have to discuss the safety. Now just quickly, the way that works is if your delta p is staying the same, your numerator is staying the same, but your denominator is getting bigger, then like any fraction, if the denominator gets bigger, the value of that fraction gets smaller. Okay, so if you're keeping delta p the same and increasing delta t, then your f must get smaller. Easy as that. Okay, last part, and this is about energy. Question 3, energy. A rider and bike with a combined mass of 85 kilograms climbed 4 meters vertically in 3 seconds while biking up a track. 3a is to calculate the average power required. Now the equation for power is energy divided by time. Because we're climbing up 4 meters and we have no other information, it's apparent that the energy involved is going to be gravitational potential energy, EP, which is equal to mgh. And because it's a power still, we're dividing it by t. We simply throw all those numbers in, because they're all the values we've been given, and you can work it out. 85 times 9.8 times the height, which was 4 meters, divided by the time, which was 3 seconds, and work out your answer. And you should get 1010.6 recurring watts, which if we round it to 3 significant figures becomes 1110 watts. Now you don't have to actually put the GP equation into the power equation, you can just work out the gravitational potential energy and then divide it by time if that's what you prefer, but I think it's always cleaner to do it all at once, like that. Merit for the right answer: if you worked out the potential energy correctly but failed to do the power, or made a mistake with the potential energy but then did the subsequent power bit correctly, you get achieve. If you do both steps correct, it's 1110, sorry. Now, part B, the rider bikes over a 4 meter long bridge and stops 3 meters from the end. The bridge has a uniform mass of 700 kilograms. The combined mass of the rider and bike is 85 kilograms. State the conditions required for the bridge to be in equilibrium. So, we have got the sort of information that leads us to think we're dealing with torques. The first question, however, isn't to calculate anything, it's just to state the conditions required for the bridge to be in equilibrium. No net torques, no net forces. The bridge is not rotating, therefore there are no net torques, or the resultant torques equals 0 Newton meters. Newton kilograms. No net forces means no resultant forces either. Same idea. Everything's balanced. That's it. To get achieved, you have to say both things: no net torques or no net forces, or forces are balanced, torques are balanced. Any way of saying both of those points gets you achieved. If you miss out one of them, you get not achieved. Now part C is to draw labelled arrows to represent all the forces acting on the bridge. We were told that the bridge has a mass of something or other, 700 kg, and we are told that the bridge is uniform. That means it is symmetrical. And so the 700 kilograms, or the 700 lots of G newtons, are acting precisely halfway through. So I'm going to have my own little addition just to remind myself that it's 2 meters to the middle. We then got the cyclist, and he had a mass, or they had a mass, sorry, of 85 kilograms when combined with their bike. So I'm not writing gram newtons, it's just 700 lots of G, remembering that weight is mass times gravity. Now we've said that there are no there are no net forces acting on this bridge, and so there must be something pushing up, and we've got these two support forces, SA and SB. We don't know how big they are, so we're not going to do that. Now, part D. Calculate all the values of the forces, calculate the values of all of the forces acting on the bridge. So, I'm going to first of all work out the weights. Weight of rider equals 85 G, which equals 85 times 9.8, which equals 833 newtons. Then the weight of the bridge is 700 G, which gives me 6860 newtons. So immediately I have got two forces worked out. Now, in order to work out the other two forces, we needed to work those forces out, and because they are opposite ends of a bridge, hopefully it's apparent we're going to be looking at doing torque calculations. It doesn't matter which way around you do this. I'm going to choose my support force as being, my pivot point as being at end A. So I'm going to say pivot at A, just to let the examiner know what I'm trying to do. If the pivot is at point A, I'm going to work out all the torques acting clockwise. And if this is my pivot point here, any force that is turning my bridge in a clockwise manner like that is going to be included here. My cyclist mass, 85 lots of G, 833 newtons, is acting clockwise. And because the bridge is 4 meters long and they are 3 meters from the far end, it's only a meter, therefore, to the near end. So the pivot at A is going to be, the first torque is 833 times by 1. Then I'm going to have my second torque due to the bridge itself, same idea again. The weight of it was 6,860, and the distance this time was 2 meters, like that. Then we can work out the total torques acting clockwise. 833 times 1 is 833, plus 6860 times 2. So, clockwise I have 14,553 Newton meters. Then acting anti-clockwise, the only torque that is acting anti-clockwise, the only thing stopping this bridge from turning clockwise, is the support force at B. Now the equation for torque, should have written it down here, is force times distance. I don't know the force, the support force at B, SB, but I do know that it's 4 meters away. Now, the bridge we've said already is an equilibrium. If you don't want to try and write equilibrium, often you can just get away with writing EQM. But equilibrium's there as well. Bridge is an equilibrium, which means my anti-clockwise torques are equal to my clockwise torques. Therefore, 14,553 is equal to 4 lots of SB. Therefore, SB is equal to 14,553 divided by 4, which is 3,638.25 newtons. So now I have worked out my SB. I'm going to put it in a box to highlight to the examiner where I have worked out a good answer that is important. Now, there are two ways you can go about doing the second support force. You can either change your pivot point to be at end B instead, and do this very similarly, a similar calculation to work out the force of SA, with the same sort of working, essentially repeated again, but this time from the other viewpoint. Alternatively, a slightly quicker way is, because the bridge is in equilibrium, the forces upwards must be equal to the forces downwards. So if you resolve all your forces, you should find that you can work out SA just because it's the last one missing. So my forces upwards are SA plus my other support force, 3,638.25, and they must be equal to, because this bridge is perfectly balanced, it's not pardon me, sorry, it's not accelerating upwards or downwards, so the forces must be balanced. The two forces downwards are the weight of the rider and the weight of the bridge itself, 6,860. To get SA on its own, I'm just going to take away this from both sides, minus 3638.25. So then I can just work out my SA with some simple addition and subtraction. 833 plus 6860 minus answer gives me 4,054.75 newtons. Now, because the question has given all of our data in two significant figures, we probably should round them off, and so my SB I will round to 3,600 newtons, and my SA I will round to 4,100 newtons. And I'll put this in a box as well. Boom. If you find both support forces to be these two numbers, that is excellence. If you make one little error somewhere in your working and all this working, that takes you to merit. If you are able to calculate a single torque correctly, that is enough for achieve. So, working out one torque is enough for an achieve mark. Then to get merit, you have to do this entire series of working. Excellence is for getting both answers correct. And that's the paper.